Hello, my name is Angel, and I'll be walking you through Method 1, the calculations and experimental portion of our heat transfer project. This method was completed alongside my teammates Julia, Parker, and Devin, each taking a different method of their own. For our study, we used a London broil cut of steak, chosen for its lean composition and relatively uniform thermal properties. This steak was cooked in an oven set to 250 degrees Fahrenheit, with the goal of reaching an internal temperature between 115 and 120 degrees Fahrenheit as part of a reverse searing process. Before cooking, the initial internal temperatures of the steak was recorded at about 56 degrees Fahrenheit. Once the oven was preheated to 250 degrees, the steak was placed inside. Every 4 minutes, the steak was removed briefly to measure both the internal and surface temperatures. In the video shown, we are taking the steak out for one final time, ensuring we are placing the probe at the geometric center of the steak and giving the thermometer a few seconds to stabilize. The steak finished heating up to 122.2 degrees Fahrenheit at its core and 116 degrees Fahrenheit at its surface. Halfway, at about 14 minutes, our core temperature and surface temperature seem to converge, or line up pretty evenly, and after that, they're pretty much the same. That got our team thinking about buyout number and lump capacitance. Here to the right is our blockpad calculations that I used in order to calculate that. As an initial guess, I used 7, which got me to a 0.321 buyout number, which is just slightly over what we needed it to be in order to use lump capacitance as an assumption. However, at the end, once I got our true H value, I got a buyout number of 0.269, which meant that lump capacitance could be assumed in our case. The geometric properties of our steak, as you can see to the left, I transferred them to the block pad, which includes the thickness, the average width, which I used as my L value, and the thermal conductivity of the lean beef. As for the oven, I used the temperature of the oven, 250, to be my surrounding temperature, and the final temperature of the steak to be the surface temperature. As for V, this stands for simply kinematic viscosity, and was needed as the equation shown in the FE manual to our left here now. K of air is the thermal conductivity of air, and G is gravity. Now to calculate for our H value, we needed to calculate our Rayleigh number. This was necessary for a long horizontal cylinder and a body of stationary fluid, which is what we simplified our steak to be. Here we see that the Rayleigh number equation is shown here, and what is necessary for that is the coefficient of thermal expansion. This is what we see here, with 2 over the added temperatures, as shown in the FE manual. Now using that, and using the other numbers involved with our givens, as well as Prandtl's number, which is 0.7 in this case, we get a final Rayleigh number of 974,485. This number is important because as we come back down here, this chart shows that we fall in this range, which leads to a C value of 0.48 and an N value of 0.25. These numbers are important, as shown here, because they will calculate our Nusselt number. In the end, we got an H value of 5.873.
Hello, my name is Julia, and I was responsible for Phase 2 of my group's Intro to Heat Transfer final project. Our goal is to study a steak on an aluminum tray baking in an oven with the goal of reaching steak core temperatures of 115 to 120 Fahrenheit. I identified 2 main ways that heat can be transferred to the steak: convection and radiation to the exposed surfaces of the steak, and conduction from the tray making contact with the bottom of the steak. Heat is also being transferred to the exposed bottom of the tray via convection and radiation. Our oven was set to 250 Fahrenheit, so I have 250 Fahrenheit temperature sources depicting the T surroundings and T surfaces of the oven for all convection and radiation values. For the convection and radiation to the exposed surfaces of the steak, I have a combined area of 0.03508 meters squared, which includes the top and side surface area of our steak. For convection to the steak, I have a heat transfer coefficient calculated in a previous phase of 5.873 watts meter squared Kelvin. For radiation to the steak, I have a radiation coefficient equal to the emissivity of lean beef, or 0.95 times Stefan Boltzmann constant. For convection and radiation to the bottom of the tray, I have an area of 0.01691 meters squared, which is the area of the bottom of the steak, since we do not assume all heat transfer to the tray goes straight to the steak. Once again, I use a heat transfer coefficient of 5.873 watts over squared metered Kelvin for my convection to the tray. And for my radiation to the tray, I use an emissivity typical of aluminum, which is 0.8, multiplied by the Stefan Boltzmann constant to get my radiation coefficient. Our tray is 0.125 inches or 0.003 meters thick, with a thermal conductivity of 177 watts over meters Kelvin. The relevant area of our tray is still equal to the bottom of our steak. Our steak itself has a mass of 0.467 kilograms, with a specific heat of lean beef, or 3,540 joules over kilograms Kelvin. Our steak also has an initial temp of 56 Fahrenheit. Running our model gives us an estimated baking time of 800 seconds to reach our core temperatures of 115 to 120 Fahrenheit.
We will now begin the SolidWorks portion of this final project. So for this first section, given the dimensions we had from when we measured and cooked the steak, at Devin's apartment the first time, I created a one-to-one recreation in SolidWorks, right? Fillets, chamfers, even the pink hue on the steak to make this as accurate as possible. Now, it seemed like a good idea at the time. Ultimately, I figured and I rationalized that a more accurate SolidWorks model, as close as I can get it, would lead to the best results. And it is, and it will in normal context. The issue arose when I went to mesh this, because there are so many little tiny corners in here. You can see the extreme number of points that SolidWorks is having to insert to try to fully define this steak. And ultimately what that means is that every time I try to hit run or mesh this material, the SolidWorks is having to calculate millions and millions of little points, and it was slowing down the simulation to the point that it was not worth it for the 0.5% difference I'm going to see from adding all of these. So using the same temperature, convection and radiation that we used in that previous sim, right? 56 for the steak, 68 for the tray, 5.873 watts per meter square Kelvin for convection, radiation emissivity of 0.95 for the steak, and 0.8 for the tray to account for the thermometer of an organic material for the steak, and for the oxidized / dirty nature of the tray. We created a simplified model that can be meshed much easier, right? It's much cleaner, it's easier to see, and it actually runs in a reasonable time. So when you go to complete this thermal sim, you're able to get this nice clean cross section that allows you to get the gradient inside of the steak. I did personally a 30 minutes with a 10-second snapshot here, and if you probe bits of your steak and calculate the average temperature over time of this cross section here over the 30-minute time period, at the end of the time period you get 164 seconds roughly, or 164 degrees, sorry, I should say, and you get an equivalent cooked temperature of about 150 at 890 seconds, which, given the fact that this steak is really close to lumping with a lumping value of 0.275, if I remember correctly, it is not surprising that it takes much longer to cook when compared to Julia's block pad sim.
All right, thank you for that, Parker. I will now walk through the transient analysis of our steak and tray example. And we can see, using the transient explorer, how this steak heats up over time. Just to go through some initial conditions, the tray started at 68 degrees, that was room temperature. And the steak had just come out of the fridge. It was around 56 degrees, so it had been sitting out for just a little bit before we started cooking. And we have some pretty predictable behavior here. So the tray heats up first, and it heats up very quickly, and it actually goes over what I've set the scale out. I set the scale to max out at 200 degrees Fahrenheit, just so I could have more fidelity at the lower end. But that was to be expected, as the aluminum is a lot more conductive than the steak. And then as far as heat transfer into the steak, you're going to have heat transfer from the pan into the steak, but also mostly the radiative heat transfer. The heat starts towards the edges and slowly moves towards the center. And after the full 30 minutes, our actual steak reached around 122. And in my transient example, we reached around 165. And I will pull up this graph. And looking at this graph, we can see how the temperature rises in the steak over time. Fairly linear pattern, never reaches steady state, again, because we pulled it out of the oven before steady state was reached. And right there reaches about 165. As I said, this is all very typical behavior. The heat gradually goes towards the center, and we reach, like I said, an internal temperature of the steak around 165. I put a probe or a point goal right there in the center of the steak to get that temperature. The last thing I wanted to cover in my transient analysis was the flow trajectories of the fluid throughout the cooking process. So this was at the last time step. So this is right at the end. And we can confirm that this is natural convection for one main reason, in that the velocities are very, very small. They're below a quarter, which is typically what we see with natural convection.
To conclude our design study, we compiled the results from all four methods and plotted core temperatures over baking time. As expected, the most accurate methods used Solidworks, as it allowed us to better represent the complexities of our problem's geometry and apply more precise initial conditions. Our Simscape method applied a lot of assumptions, which could lead to skewed results. That concludes our Intro to Heat Transfer final design study. Thank you for watching.